Hello, Jordan.
Hello, how are you?
How are you?
Pretty good. Coming to the close of the semester, huh? It's almost over.
Yeah. But we still have the midterm in quantum on Thursday.
On Thursday. Yeah. Yeah, that's gonna be tough.
Yeah.
The midterm at the very end of the semester, right?
Yeah.
But hopefully he doesn't slam in one more exam before the final. Hopefully it's just the final after this.
Yeah, I think it's just one midterm.
Is it in class?
Yes.
It's gonna be tough, I'm sure. Best of luck on that. That's all I can say. These exams are hard whenever I
Hello?
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 Why is the volume so low? How do you change the volume? Jesus. Oops. I don't want it. Oh, come on, come back. Give us a few seconds, Jordan. Yeah, I accidentally switched off the monitor. So. Can you say something so that we know whether we can hear you or not?
Hello?
Yeah, we can hear you. Still low a little, but yours is all usually low.
That's odd. Yeah, that's very odd.
Some HDMI 1 or something. Oh, here we go. Something.
Yeah, I didn't. What?
That's pretty complicated.
Yeah. All right. There we go. Okay, cool.
Okay.
It was the AV mode button, which is right there.
Oh, wow. That's not very obvious.
Yeah.
Audio video mode, huh?
Yeah.
It's usually HDMI. Or, yeah.
Well, it was already on the HDMI input setting, but it had to be on the
AV mode.
Yeah.
So I shouldn't press on that now, right? If I press on that now, it will go away.
Probably if you press. Well, I don't know. You could try it.
No, it will take another 3 minutes to fix it. I don't trust my knowledge on these things. Okay, I'll keep it for my instincts on these things. Okay.
I feel like there should be a way to play it through the speakers too. Like,
Isn't it playing through the speakers?
well,
Oh, you're saying these
those, yeah, I think it's just using the internal TV speakers, which are not that loud.
That's here. There is something. So I increase the volume now. And audio mute this?
Try it. I don't know. I just like max.
Jordan, you want to say something again?
Can you hear me?
That's all. That's better. Definitely.
That's much better. So I increase the volume.
Okay. Yeah.
Okay.
That's a lot better. Yeah.
So good thought. But we don't know whether it's coming from the speaker or not, right?
I guess. Yeah. I don't know.
Yeah, but this is sufficient.
Yeah.
Okay. So there was a homework due today, apparently, which was probably due earlier.
No, today was the actual due date. I think.
It was actually due today, okay.
Their homework 8. Yeah.
Yeah, homework 8, okay, it was, okay. So homework 9 will be, so before homework 9, I should say. So there's a small thing that has come up. So there won't be class on April 20th, Tuesday. So no class. It's not the best thing when we are struggling for some time, but we don't have much choice. So, homework 9, which has not been uploaded, but I'll do that soon today, will be due. So it would have been due on 20th, but since there is no class, April 22nd, Thursday. Oh yeah, this is also a small change. Again, I thought over this. We're going to have an in-class exam. There are reasons for that. I did thought so. We're going to have an in-class exam. Okay, Jordan. So just one day. It's a final exam. So.
Okay.
Okay. So we have the Green's function now, basically the electric potential due to a point charge, not only when it is at rest, even when it is moving, we have a contribution from it at each instant. And now if we add up all this, if we superpose them, we can get it for a moving charge in principle. And we will see that it is reasonably complicated to do that, even for a uniform charge. So let's explicitly do this for a uniformly moving charge. Just no acceleration. And let's see how it goes by. So this is a uniformly, or does uniformly moving charge mean uniform velocity? No, right? Probably not. Charge moving with uniform velocity. We're talking about a positive charge. There's nothing else. It's moving with velocity v along the z-axis. Now there are two ways of doing this problem. Now that we know Lorentz transformation, we just have to go to a frame which is at rest with respect to this. We know what the field is. Electric field is there, magnetic field is 0, right? Because it becomes a static problem, right? So that's a very easy problem to do, but we will do the complicated way and show or interpret it in terms of Lorentz transformation. Okay? instead of doing this short way, we'll do the long way, especially so that we know how this goes through, like even for the simple velocity problem, how this whole problem goes through. Is that clear properly? What we are doing? Okay. So we have the position of this charge is, let's call it RQ. So this is charge Q, right? Moving with velocity V, and let's say this is the axis. The position of the charge at time t, let's say, is 0I plus 0J plus, it's moving with time. So let's say at time t equal to 0, it was at the origin and it keeps evolving. This is in some reference frame, a fixed reference frame, in which in a lab frame, let's say, where the charges are moving. We will need this for time t prime. So, but now I think we have got comfortable enough going from t to t prime. So let me not change. If you want, yeah, let's be consistent. So this is t prime. Same thing. Velocity of charge q as a function of t prime is 0I plus 0J plus velocity v in the k direction. That's a description of the motion. Charge density as a function of r prime and t prime is equal to charge itself. Wherever the charge is, there is a delta function. So there's q times x prime minus 0, y prime minus 0, and z prime minus vt prime, which is the position of the charge, right at that point. There is a function. Current density is usually just v, charge velocity of the charge itself as a function of t prime times the charge density, which is the same as q times v in the direction of k hat times delta of x prime, delta of y prime. I stopped writing 0, that was just to convey the point, but it is the position of the charge. That's your charge density and current density. Yes.
Is that T prime in the charge density?
This one, right?
The second one?
Here?
No, the over to the right.
Here?
In the charge density.
In
In the charge density.
In the second,
And
Oh, yeah. Oh, okay. Sorry. That took a long time. Sorry. Okay. Thanks. Okay. Okay, so that's our problem. And what's our, how do we want to get the potentials, scalar potential to begin with? At some observation point r and t. So remember that's a some r at some time t, right? So that's r at time t. To make an observation, this time there is time also playing a role. So that's 1 over 4 pi epsilon naught. And leave some space here. I'm going to change things. So there's a little space here. d cubed r prime. And again, leave some space here. So that's r minus r prime. And rho of r prime, comma t prime, right? If you were doing statics, there is 1 here, and there is no p prime here. But now our Green's function has changed. Here, first of all, add not only all the source points, also the times at which the source was emitting, or times at which the source was existing, you can say. And the Green's function, or the electric potential due to that point charge, there is a new contribution, which basically selects the time. And that's basically R minus R prime over C. That's a change. So what does it do? Immediately one would say that, oh, is there some mistake here? It seems to suggest that T prime, so remember T is observation point, but we seem to be integrating T prime even in the future. We're going all the way to plus infinity. Plus infinity is in the future. That's not causal. That seems to suggest that a future can affect you. But it's not really, because this delta function makes sure that only a particular time is selected. So it's not really, this shouldn't be misinterpreted that it is actually the future contributing. It gets contribution only from one time, or not necessarily one time. It seems like it is one time, but remember there could be time inside of this also. So that could be more than one time. It could be a complicated path, but in general, selected times, which always should be causal, only causal contributions should come in. So with that in mind, and we will see that how this starts contributing. We will see that it seems like there are two contributions, but then we will see, oh, we are having a non-causal contribution, so we'll subtract that out and get this. So keep track of all this. So that's your, oh, am I out of the, no, good. So vector potential, similarly, is mu naught over 4 pi infinity to plus infinity dt prime same thing, except that this time it is the current density that acts like the source. So that's G. So I'll start working the scalar potential, but you will notice that this is almost identical, right? If I replace J here, Q times V is the only thing different, or V times K hat is the only thing different. That comes out of the integral completely. So this is nothing but, if I can write one step down. So that's V times K hat times the scalar potential. If I don't really have to do the double work. Oh, is that really true? Probably not, right? Because I have to pull out this mu naught and put in that epsilon naught, right? So not really. So this is mu naught times epsilon naught, which gives you 1 over c square. So that means this is V over C, which is beta, right? Beta times K hat, which is correct because A and phi are pieces of the same Lorentz quantity, right? Over C, right? That's the way to write it, right? So it's better. So this beta is V over C, remember? So that's a better way. Yeah, good. Okay, so we have constructed or posed the problem now. Let's try to do the integrals. When you substitute the charge density, there are 3 delta functions that come up, and then there is another 4th delta function in time. 4 integrals, it seems like it should be straightforward. Right? For usually delta functions are straightforward to do. But here we will see that there will be slight catch. So let's see. Let's proceed. So this is phi or t. Writing this more explicitly, pretty much replacing it, but in a more explicit. So dt prime. This is dx prime y prime, z prime. All that is okay. And I have delta of t minus t prime minus 1 over c. This distance actually is the same distance that shows up in the denominator, is x minus x prime square plus y minus y prime square plus z minus z prime square. Same thing here, x minus x prime square plus y minus y prime square. And then there is a charge q, I pull it out. And then there is delta of x prime, delta of y prime, delta of z prime minus vt prime. Plus writing everything in very detailed. So 3 of the x prime, y prime, z prime is doable, but the moment you do z prime integral, it couples it, like z prime goes into the z prime, and that's the challenge. We'll see. So that's q over 4 pi epsilon naught. There's only time remaining then. And the integral is delta of t minus t prime 1 over c. X prime is gone, so this is x square plus y square plus z. Z prime gets replaced with bt prime. And divided by x square plus y square plus z minus bt. Right. Okay, so that should be, one would think, or at least we have pretended as if delta functions are the easiest integrals to do this, but we cannot do this, right? We need to know when does this argument go to 0. Right? Whenever the delta function argument goes to 0, it contributes. But this is not a straightforward equation, but not undoable either. It seems like this is a quadratic equation, right? So there will be 2 values of t prime. So let's remind ourselves of how do you do such an integral. So remind ourselves that if there is this I'm writing in dx, if there was a function of, let me not write it as an integral either. So if I have a delta function of an function f of x, right? What is that equal to? Have you done this?
That'd be f of 0.
Huh? Yeah, we are to find the roots of f, and then suppose we find, let's say we know all the roots of f. So x of r are the roots. Then what? So r going from 1 to 3. Like if we know the roots, what is this equal to?
F of root 1 over root 1 plus f of root 2 over root, is that right?
F of root 1.
Wouldn't it just be the delta function divided by the function, or divided by whatever variable in the function there is? So x, delta function of x over,
Delta function of x.
yeah, over, I think I remember when we did it, it was like the
minus,
absolute value of whatever the,
yeah, good. Absolute value.
of, I don't remember.
That's the derivative.
Yes,
Derivative
derivative. Yes.
XR.
So you have to find the derivative of the function at x equal to xr. Okay, and then take the magnitude of it. So there could be more than one roots, so then you have to sum over all the roots. So example, just to clarify how you do this. Example will be, so let's say delta of let's say quadratic equation that's doable, x minus 2, x minus 3, so let's say x squared minus 5x plus 6. Right? So that will be equal to, the two roots are 2 and 3 here in this case, so you would say, oh, x of r is equal to 2 comma 3. So this will be equal to delta of x minus 2 divided by, take the derivative, so that's 2x minus 5. Evaluate this at x equal to 2, and then take magnitude of this, or plus delta of x minus 3, and then take the magnitude of 2x minus 5, evaluate that at x equal to 3, and that gives space. That's equal to delta of x minus 2 of 2 times 2 is 4, 4 minus 5 is minus 1, that's 1. Plus delta of x minus 3, 2 times 3, 6, again 1. Okay. So the strategy then would be that you find the roots of this, correct? And then find the derivative of that and divide it and so on. Okay. So let's define. So let's define not this area. So let's define f of t prime, not t, to be t minus t prime minus 1 over c x squared plus y squared plus z minus vt prime squared. We have to find the roots of that. So let's say we will call the roots of this function as the retarded time. So we will, whenever that goes to 0, at whatever time it goes to 0, we'll call it r. So at the time when this goes to 0, we'll call it tr. Right? That's the root if you want. And the derivative of f, since we are interested in that, is equal to t prime with respect to t prime, right? And then we are evaluate it at t of r. So derivative of with respect to t prime is minus 1, and then I take this minus 1 over c, 1 over 2. This goes in the denominator. I'm taking a derivative with t prime. So it brings in a 2 in the numerator, z minus vt prime. And then I will do a minus v there, right? So multiply to the minus v. So that's your derivative. So it's 2 cancels out, this minus becomes a plus. So that's minus 1 plus v over c. Okay. Notice that the second term in here, v over c is always less than 1. And the next term, z minus vt divided by square root of something, that has a z minus vt plus something. So this is also less than 1. So second term is always less than 1, which means that this, as it is written, this is a negative quantity. So, when we take the magnitude, anyway, we have to take the magnitude, so it is 1 minus that we have to take care of. So let's say the f by dt prime at t prime equal to t of r is equal to 1 minus, or we'll write it as, we'll always pick the positive. C okay, that's what it is, correct? So we are now having all the ingredients to do this integral. Let's substitute it back in there, do the integral. But we still have not found the roots. Remember, we pretended that we have the roots. We'll see that that's just a quadratic equation. But pretending that we have it, let's proceed and let's do the scalar potential equal to 1 over 4 pi epsilon naught. And when we do the integral, so this is 1 over, so x squared plus y squared plus z minus vtr squared. First replace the whatever the function is with tr, and then get a scale which is basically f over dt prime, evaluate t prime equal to tr, and then take the magnitude. That's what it is. Right? So that's the same as 1 over 4 pi epsilon naught r whole square. Right. And then this is 1 over 1 minus v over c times z minus vtr over x squared plus y squared okay. Multiply this out, this cancels out. This is equal to so that's equal to 1 over 4 pi epsilon naught 1 divided by x squared plus y squared plus z minus vt squared minus v over c times z minus vtr. That's it. If you want, that's the it. But let's do one more trick here. F of tr is equal to 0 means that t minus tr minus 1 over c times x squared plus y squared plus z minus vtr is equal to 0. Right? That means that this is equal to t minus tr, so that means I can replace this with t minus tr. That's just a trick. Otherwise, I had to evaluate ER and do thoroughly more algebra involved. If I replace this at this stage, it leads to a little simplification, but it's just a way of doing nothing. Oh, am I in the? Oh. Okay. So substitute this in there. So phi r comma t is equal to 1 over 4 pi epsilon naught 1 divided by. So this is if you want c times t minus tr minus p over c z minus vtr. And it is possible to show that this is a Lorentz invariant construction, but that seems not very insightful here. But we will not go and worry about what structure this is. Actually, there is a structure. And, so let me pull out the C there. So that's 1 over 4 pi epsilon naught. So basically divide by the C. So 1 over C. 1 over C. 1 over oh, yeah. Okay, so I think that's what we. It seems like how we do that, right? So let's at this stage we have to find the roots, and let's proceed to find the roots. So for finding the values, we go back to our f of t prime. So this is and we say that t minus t of r is equal to a square. Square of that is equal to x squared plus y squared over c squared plus z minus vtr squared over c squared. So that's a quadratic equation. Let's try to get that equation. So t squared plus t of r squared minus 2t of r is equal to x squared plus y squared plus c squared plus z squared. And then minus plus v square over c square times t of r squared, and then minus 2 z over c v over c times t of r. Plug them all as a quadratic equation, so that's 1 minus v squared over c squared times t of r squared. That's this term gone, this term gone, and then we have minus 2 tr, and that's t, that's this term. And this goes on the other side, that becomes a plus. If I return it as minus, it's minus of 2 is taken out, so it's z over c, v over c. That's also done. And what we have remaining is just this is r square over c square, but we want to, there's a asymmetry in x and y. Minus, I think so. Okay, but So that's your quadratic equation into your part. Let's see, A, B, and C. So what's the solution for a quadratic equation? It's minus B and divide by 2 times A, right? So the 2 is not needed. So it's minus, so it's T minus Z over C, V over C, and plus or minus square root of P square. That's P minus V over C, V over C the whole square. Let's square this and actually that should be a 2 times that also, but there's a denominator that's a 2, so I'm canceling out. And 4AC, that's A is minus and a minus that's gone, so it's remember that. So 1 minus B square over C square and square of Y square over C square plus. Oh.
Is there a T squared? I just noticed in the top, in the second line.
Oh, there is the T square. Good. Thank you. That should be a plus T square, right?
Yeah.
So it seems like this was, yeah. So that's good. Thank you. There was struggle at a late stage. So what I missed is that this T square times, yeah, it should be here, right? This should be plus 1 minus B square over C square, and this should be minus. I think that's what should be. Thank you very much. I missed this. Yes, I have done big one. This is 1 minus B square.
Is there a,
Yeah.
the second term, the minus 2 P sub R? So shouldn't that minus 2 be in the first term of the quadratic?
Oh, here? Yes, but that is usually you divide by 2 times A.
Okay, you left that.
So I left out the 2, and then this 2 will get squared. There's a 4 there, and there's a B square minus 4AC.
Okay.
So I did some one step.
I was writing while I was going on.
Yeah. So this is if you have x squared plus 2bx.
Yeah,
plus
I see it
b
now.
To the 0, so yeah, this is minus b plus or minus b square minus ac, right, divided by a. Okay, so let me write this with that because you know there's a t minus b square over c, they come together. So this multiplied by that is what actually we need. So let me write this as t to the power is actually equal to. There's a small simplification, not significant one, but still that's all we write because there is asymmetry in the problem. X and y and z go differently, so we have to live with that. Okay, so expand this out. There's a t square coming from here, which will cancel the t square from that. So let me expand it. Let's write it. Plus z square, c square, v square, c square minus 2t z over c, v over c. Keep this intact. How much can be done there? Square. And this one expanded. So it's plus v square over c square minus v square over c square, v square, c square, minus g square plus. And the board is some tiny cancellation. Significant numbers. This square cancels out. And after that, whatever is remaining, the three terms with t, they all come together as square. So this is equal to t minus v over c, v over c, plus or minus x squared plus y squared. Let me take a c out actually. Everything has a c squared. 1 over c out. There's x squared that's this term. And the remaining three terms, v over c, this and this, have a pattern, which is basically v minus v t. This one. Again, you get the z minus vt form, but notice this Lorentz factor came together with the perpendicular components of the position. Right. So, what we can since we have the structure in this form, let me write this as t minus z or yeah, what should I do? It's okay. T minus 2r. Yeah, let's write this as p minus 2r. So it's t minus tr. And then the minus v over c times z over c minus, so that's, I come this term plus, so that's v over c. That whole thing is this minus this. So that's the same as putting this onto the left. Oh, I should actually first decide which plus or minus, right? As of now, minus plus 1 over c square plus y square minus v square over c square plus v minus v square. Which is exact, so this left hand side is exactly the denominator that shows up in that expression for scalar potential. So if we replace that with this, that's called scalar potential, which is fine. You can write it in this form that P of R is function. There are two roots here, this, right? Then it raises the question, are both roots okay? So there are two roots. Let's set v equal to 0 and analyze it. So v equal to, so come back here. Right, come back here and argue that at v equal to 0, what are they? What are the two roots? And v is equal to 0, the roots are t of r is t plus or minus, when v is equal to 0, everything should go away, and that's just r over c, right? And then we ask what should this be. Remember that what is this retarded time? Where will this go? Let's see. Where is this supposed to go? Like we are saying that at what value of t prime is this going to contribute? Right, t prime is associated with the source, right, and observer is the time t. So the source should always be before the observer. So if TR is plus, that means that's not causal. So if I say this is plus and that is T minus ROC, so this is not causal. And this is causal. And at this stage, if you notice, you're dropping it by hand. Mathematically, it's allowed to have the two solutions, but you drop it mathematically. So you drop this on causal. Just because we don't like it, we cannot comprehend that pretty much by hand. Drop it. And if that's this is the correct one, so this is the right one. So that's minus, which we have kept. So when you take it to the right hand side, this minus becomes a plus. This is a plus solution. Okay. So this is a minus one, and I take it to the left hand side. So let's say a physical argument that goes through. And once we have that, we have the scalar potential. So the scalar potential then is scalar potential that means or T is equal to, put a that in there, and that's 1 over 4 pi epsilon naught, 1 over square plus y squared, 1 minus b squared over c squared, plus z minus dt. It is good to have one interpretation here. So if velocity v is equal to 0, that's straightforward, right? That's your static, no doubt about it. If v is equal to 0, so v is equal to 0 is static, like static situation, no doubt about it. That's a clear indication. But there is one more interesting feature, that if you take c tends to infinity, like that means the finiteness of speed of light was not there. That means signals could actually go instantaneously, whether like all the starlight that we see are actually instantaneously coming from the other galaxy to us. Then what we have is that this term goes away, and it is like as if the charge is moving and we immediately get all the information. So the position does change. This still, there is time dependence in there. It's a very trivial time dependence in the sense that as the charge is moving, we get all the signal immediately. Nothing wrong there. So that will be action at a distance, right? So this is what, so this is action at a distance. And this is, I mean, just to mention it, I mean, since whenever there are this, in quantum mechanics, when sometimes we deal with interpretations where if you have an entangled state, you make measurement on one and you get the measurement on the other as immediately known. There is no speed of light because quantum mechanics often does not include the electromagnetism in there. This is pure measurement problem. There, how do you get the information from one to the other? That's why you often say action at a distance problem. So that's this feature where C is defined. So the information goes from one point to the other instantly. And that's typically not acceptable. And that was the complaint Einstein had with respect to quantum mechanics in the famous EPR paradox, which quiz. Just a few lines, don't go too far into it. So quiz is what's the discussion of action at a distance in quantum mechanics and in Einstein's EPR paradox. Okay, and of course, I do want to mention that I have done two calculations simultaneously, right? This is beta times k hat times phi of RT. I've done that, completed that, and over C. And in the Lorentz sense, you would say that, oh, electric potential gets behaves in such a way that the distances, how far your x and y gets not contracted, right? Yeah, x and y get contracted because there's gamma in the denominator, and z stays the same. Like that's the way to see it. But let's interpret the electric field and magnetic field instead of interpreting electric potential and vector potential. Okay. Any questions at this stage? So now we go to electric fields and magnetic fields.
Just
Yes.
a quick question.
Yes.
I don't immediately see why, like just from looking at this equation, why C to infinity implies like, oh yeah, so like why, when that term drops out, why does that immediately mean action at a distance?
Because, let's say, because at time t, the position of the charge is at z, correct? But you're observing also at the same time, right? Observation point is at t, and the charge is also, like if you were to think of it as static, think of electric potential due to a point charge, x squared plus y squared plus z squared, right? If I were to replace this with z minus z of charge, which is Vt. So that exactly gives me that. Is that okay?
I think, couldn't you just say that as C goes to infinity, there's no such thing as retarded time? So the transmission rate between some distant galaxy that would take traditionally with a maximal speed of C would take some extra time to get to you would be transferred instantaneously? Is that what
That's
you're saying?
correct, but that's what Luke is questioning. Why? How am I able to conclude that from this expression? That's Luke's concern.
I'm not too bothered by it because like when you have the retarded time explicitly, it's yeah, I'm fine with that. I was just wondering
If there is a better way of looking at it.
yeah, just strictly on that equation.
I was just thinking it is because it is if I have a point charge y square plus z minus z cube square, right? That means the charge is at z cube in statics, right? But now I'm saying this is x, y, z, and t, right? So this is Vt. That seems to suggest that, oh, the charge is at time t, it is at this point, and I'm observing it at also at the same point.
Okay.
So maybe,
Yeah.
maybe it is not, I don't have more than that, but maybe there is a better way of saying this. But that's all I meant, and that is, that's all. That's all. Yeah, I also agree. It's probably correct, as Jordan is saying. But yeah, I don't have a better way of saying it. But let's proceed. Hopefully, electric field is slightly more intuition, because then we want to actually see how does the electric field look like for a point charge. So, okay, so this probably a lot of the electric field is now it's all at actual observation times. Electric field is gradient, negative gradient of phi minus dA by dt. And magnetic field is saving space. It's del crossed with A. So it all involves derivatives with x, y, and z of t. Right, that's what all this involves. So first let's see what is the derivative of the scalar potential with respect to x. Correct. So if you notice, if you look into your expression for phi, in front of x squared there is a factor of 1 minus v squared over c squared coming, that's all. And we know how to take the derivative of a square root, so it will become raised to 3 over 2, and that factor shows up, and the factors of 2 cancel out. So this will be equal to, and let me also say I hat times this, because as a gradient has this I hat. So that's going to be equal to 1 over 4 pi epsilon naught times x times or I hat times x over x squared plus y squared 1 minus v squared over c squared plus z minus v t whole square. The same thing works for y also. Maybe I can do this right here. Plus j hat times d by dy phi hat will be plus j hat y hat. Oh no, there's something missing, right? What am I missing?
Charge.
Oh yeah, charge of course. And this is a factor of 1 minus v square over c square, right?
The minus sign.
No minus sign. Why do you say minus sign? Is there a minus sign? Oh yeah, minus sign. Yeah, maybe. Because it's a minus 1 by 2, right? Oh.
But it's
Oh, because it's a negative gradient. Yeah. You're right. Minus sign. Yeah, that's correct. So there's a minus sign to begin with. Then there is a minus 1 over v square or c square. A lot of mistakes. Right?
Yeah, on the left-hand side, though, we just have I hat d by dx, so we weren't looking at that negative sign yet, but we could put it.
Yeah, if I put a negative sign, it will be gone. Is that the one?
Yeah.
So maybe take this negative sign
Yeah.
because we're going to encounter it anyway. Good. D by dz is a little tricky. It doesn't have this 1 minus v squared over c squared, and the factors are different, right? So let me do that also.
Also, there is the power of 3 halves, right?
Oh yeah, 3 halves.
Yeah.
Yeah. Sorry. So many mistakes. For a list of mistakes. Okay. And let me do this z also now that you're doing this properly. So gradient of phi is equal to, when I do the z, the power of 3 remains the same. Negative stays the same, but yeah, negative stays the same. So negative and negative cancels out, plus k hat. This is just z minus vt. That's it. So that it doesn't get the contribution from 1 minus v square over c square, apparently. But it will be that. And the same derivatives will enter into del cross A also, which I will, to save time, I'll leave it to you guys. but we'll have to do the electric field. Rob, you had concerns? You were looking
Oh,
at.
no, I
Yeah,
was
good.
just
Yeah.
looking at the change.
And minus dA by dt will be equal to, remember, A has this direction beta k extra, right? And or beta over c square, right? Or v over c square. A is v over c square. So this is how do we work? So same as d by dt of this would be d by dt of phi, but with that extra v over c square. So this is dq over 4 pi epsilon naught. And same direction k hat showing up. But this time we're taking a derivative with time, so that gives you an extra minus v. So first let me write this is beta 1 over c. That's coming from the complete definition itself, and then minus v minus vt, and there's a minus v extra. Now, okay. Let me start to add this together, and you will notice that there is this factor of minus 1 over v square over c square exactly needed for this thing to come out common. So, if you so the electric field then is R and T is equal to 1 minus v square over c square, common completely, and then there's q over 4 pi epsilon naught x I hat plus y j hat plus z minus dt. This is again, so the direction doesn't change because it's very similar to action at a distance. But the magnitudes for each point change.
So doesn't the 1 minus v squared over c squared only apply to the x and y direction?
Talk again? Yeah. So this one, right?
Yeah.
But notice there is a beta over c times v is
Oh,
v
okay.
squared over c squared. That has to be added to this.
Yeah, okay.
And that's exactly that extra term.
Oh, okay.
So it makes it symmetric. The direction becomes very similar to the old.
Okay.
But in each direction, things are different. Okay. So recall again, what are we doing? If velocity v was equal to 0, you have a positive charge. It would have, this is the motion actually, that's your velocity v. And your electric field lines would have been like this. Right. That's how your electric field, again, that's our elementary first point in this course. But now things are different, right? Now we want to see how things are different. So let's say this is your z direction, right? That's your z hat. Right? Let's pick this point here. Okay. So it's a special point on the x. So this is x equal to 0. Let's say y equal to 0. There's some value of z. And let's take t equal to 0. Just to get a feel for what's happening. What happens to that? So there is an electric field here when v is 0. Let's ask what happens to that electric field when you observe at time t equal to 0. Remember, time t equal to 0 means somewhere it should have come from the charge somewhere earlier, right? The charge is moving here. If there has to be an electric field here, it will get contributions when it was before, from the past. If the star is there, what we are seeing is not the star there. We have to look back. And it's slightly convoluted.
The way you drew that, it doesn't seem like x would be 0. The x component.
How that again?
Just the way you do that. It seems like that point, the observation point, would have a non-zero x component.
Oh, non-zero x component. Yes, that's correct. Actually, we are going to do that. I think so. Yeah, I think so. I think you're correct. So that's why I'm not trying to do that too much. It gets pretty quickly harder and you have to actually be careful about it. So what I'm going to do is the following. Okay, so let's calculate at this point. Let's calculate the x component. Right? So we are doing I hat dotted with e at x equal to 0, y equal to 0, z and t. Or actually, I'm interested in the x side. Maybe I didn't want to do it. I put z also equal to 0 because z was. I think that's what you were asking. Right?
Yeah.
I think that's what you were confused. Yeah. So it's because this is z. Let's say x 0, 0. Just to get a simple quantity out of that. Okay. That's equal to, this is gamma, right? 1 over gamma square. Remember, gamma was 1 minus v square, v square in the denominator, right? So that's a gamma square. So that's gamma square. Q over 4 pi epsilon naught. And I hat will pick only this, so there is an x in the numerator, and in the denominator, z and t, everything is 0. So this is x square, and there is a gamma square again, right? 1 over gamma square. And this is called q. So that's like, if I were to really measure this, so this is not 2, 3 by 2. So one of the x's cancel out. So it's q 4 pi epsilon naught 1 over x squared. That's your electric field that you expect. And now I have to count the factors, right? There is a gamma cube in the denominator of the denominator, and there's a gamma square, so it's gamma. Really?
Yeah, that's right. 1 over root.
Yeah. That's right. So gamma is greater than 1. So the electric field component is greater than, this is still, yeah. This is greater than the electric field for v equal to 0. If I had calculated the same thing for static case, this would have been having this length, right? Just 1 over x squared. Or set gamma equal to 1 then, right? That's your, so this is greater than that. So this will expand out, right? So if I were to try to draw that now. So if I were to draw this now, so this is positive charge. So just for reference, this is my electric field lines at a certain unit distance. This has got expanded out. Right? So the field lines are longer here. That's way off. Okay? This is what is it called? contracted and dilated, right? Electric fields, like I think time you said that is grown in size. Okay. That's one, and the same thing will happen for y also. X and y behave the same way. And remember, the charge is moving out there this way. That's your velocity v. So if you think of field lines as your extended hands, right? You're moving forward, and you think of your hands as your field lines. Your hands are growing in size, right? If the length of the field is length of your hand, they are growing in size as observed by someone else, right, with respect to me move. Now let's see, what about a distance in the forward direction? Let's say I was moving like this, so this is representing my field line. Let's calculate the field line at this point, right, slightly ahead of me, like exactly the same distance there. And let's, so that would be equal to k hat now, right? Because this is expected. And let me take the k hat component of it. So let's say k hat component of the electric field, this time evaluated at 0, 0, z, 0. Did I get that right? So that's somewhere here, and the k hat component of that. So that's, again, there is a 1 over gamma square. Q over 4 pi epsilon naught. And this time k hat component, so that's at time t equal to 0. So this is z this time. And this time it is just z cubed. So that's the same as now it has contracted. And not by just contracted, it has contracted by a factor of gamma squared, not v squared. This is less than electric field v equal to 0, right? So this is squeezed in. So electric field lines, forget the velocity, we know what this electric field lines are like this. And the same thing will happen here also. In fact, field lines will be like this. And if you do this carefully, this will actually be part of an ellipsoid. The field lines are no more along a sphere, they are on the surface of an ellipsoid, if you want. Okay. That's some intuition hopefully associated with that. I cannot draw better diagrams. It would be nice if one can show that. I've not seen nice graphics related to this out there. I don't know. I didn't search either. But now, yes.
I have a quick question. So now this ellipsoid, because if v equals c, is it just a flat line?
Oh yes, good, very good. So that's your homework, I think. Yeah, that will be your homework. So not just flat line, but a flat plate. Very good. Right? If you don't want to set v equal to c because massive charges, massive particles cannot go with speed of light, but you can go very close. Let us say that it is really close. So then all this will really collapse into a plane, and this will go all the way to infinity. And you would say that, oh, this is infinite. But there is a delta function hiding in that. So you will do this as a homework explicitly, and you will show that actually this comes out as a delta function, and all the energy is on this plate, on this plane. So electric field has energy, remember, and momentum. All the energy will be on this plane, which is perpendicular to that. Exactly what you're saying, Jordan. Very good. Yeah. And this was first time realized, I think. I mean, that feature of the delta function coming out was very important. That was observed by, oh, I forget his name. I don't think. Yeah, I think in your homework you will see this example. Right? So it is not 1 over r square, it goes as 1 over r. Electric field goes as 1 over r in 2 dimensions. and this will go as 1 over r. It has to, because otherwise Gauss's law will not work, right? So it's very clean, it comes out very nicely, works out very well. So you'll see that in your homework. Okay, good. Except I didn't tell anything about magnetic field, right? So I have not done it, but you see that except for the curl, but it is first derivatives that show up. Again, you have to put this all together. First of all, magnetic field comes out to be, I should first give the expression, right? Good idea to put the expression here and then draw the diagram. So magnetic field expression is R comma T. Yes, so there's an extra beta there. Okay, so there's 1 over C first of all. So let's say C times B. I like to write as C times B. It should be this side. So there's beta times there's already a 1 minus V square over C square, which is 1 minus beta square, right? Times times is it mu over 4 pi or is it? Yeah, it's Q over 4 pi epsilon naught. Rest everything is the same except what will be the direction? If it does not change, what was the original direction?
You wouldn't have a Z or a K hat, right? You would just have
Not just have, more than that, right?
X and Y.
Yeah, very good. And with a minus sign, right? Because it has to be phi hat.
Oh, yeah.
Right? So yeah, good, very good. So if I were to draw this magnetic field in here, so originally a positive charge line, but V magnetic field is this way, right? So that's the planar one, and it gets weaker as you go forward, right? No, whatever.
No, that's right. You would get a smaller circle, right?
No, because velocity equal to 0, magnetic field is 0, right? No magnetic. Right? V equal to 0, B is equal to 0, right? Absolutely nothing. Correct? Yeah, I think maybe you were thinking I was drawing the actual finite velocity. Because
Direction.
yeah, so no magnetic field when it is at rest, but if you're observing it while it is moving, right, that's your velocity V. In its plane, there is this magnetic field. This is all in the plane. Okay. Now, as you go forward, it's getting weaker, so it gets smaller. If I have to show it like that. So then, as you go forward, direction, this is getting weaker. There's less magnetic field. That's what I'm trying to show. The density should be lower. I think that's what. So there are more field lines here, less field lines. Yeah, that's the best I can do, I guess. Is that even better? Like its intensity of the magnetic field is less in the forward direction and in the backward direction than in the horizontal or in the plane of the charge. Right? That's what I mean. The expression comes out to be this. But straightforward, it's not very hard to see that. Okay, I finished it in one part. I typically do this in 2 classes.
Nice job.
Yeah, it's good. But you guys allow me 10 minutes extra. So I can go slowly at the end. Actually, that's it. That 10 minutes, if I had broken into 2, it would have been at least 25 minutes because I would have summarized the whole thing. Yeah. Usually that's the time. But yeah.
So there's a time dilation for these final 10 minutes.
Yeah. So any questions, comments?
So I'm curious, you can do this, you can derive these formulas when you know the Green's function from the light cone itself by just drawing.
But notice, no, there is a caption here. Notice, if you had, let us say you had done this for an uniformly accelerating particle, inside the delta function, it wouldn't be a quadratic equation anymore, right? It will immediately become a quartic equation.
But if it has a constant velocity, you can do the drawing on a light cone. I
Oh,
assume.
yes.
So
And
you assumed a constant velocity.
yes, yeah, then it can be done, yes. Like now we did this whole thing explicitly, right? So here is how we will go forward. At this point, we have been exact, no approximation made because we were so confident because we know that when it is at rest, this is the old electric field. So we knew exactly what to expect. But any other distribution, any other time dependence is hard. And no one even attempts it to a certain extent. But instead, what we will do is that we will talk about radiation now. And radiation by definition would be, we will be talking about very far away quantities. Like there will be a huge approximation we'll make. Like things are happening inside an atom, right? Radiating charges are moving around. And we are going to talk about radiation. And we are going to be observing it very far away in a lab, which is millions and billions of meters away. And we'll talk about the time scale and the distance. So we'll define radiation in that sense. And pretty much in the delta function, we'll drop certain terms. In that strong approximation, it's pretty much exact to actually drop it. Like we don't lose much information. And that will let us actually talk about radiation, or we are talking about energy at infinity. What is radiation?
So you're talking about now accelerating particles as opposed to
Accelerating particles, but we will talk about electric field on the dome of our universe, right? Which is pretty much the lab. As far as the charge is concerned, its infinity is the lab room, right? You see what I'm trying to say?
not exactly,
So
but
think of a charge. There's only one charge in the universe, at the center of the universe. There's nothing else. Now, it is difficult for me to talk about the electric field somewhere 1 meter away. But in the extreme limit of R tends to infinity,
I see, okay.
things get simplified, and I talk about how much energy crosses the dome of our universe. So we will only talk about angular distribution. That's scattering cross-section. That is the definition of scattering. We don't talk about what's the energy or electric field somewhere in between, because that's too complicated. It can be done maybe for a specific problem, but in general not doable. So we'll talk about on the dome how much energy is crossing, and that won't be zero. That's what we are going to see, that won't be zero, even that 4 pi r square, that Gauss's law, even if you kill all that flux getting killed because of the volume dependence, even then something survives. And that will be defined as radiation. And we'll talk about angular dependence, frequency dependence, those kind of stuff. That's basically the idea of radar or radio communication, like radio antenna, radio receiver, all that comes in that. So we'll do a couple of examples there. So we have about what? With the missing class, I have 4 classes remaining. 1 class, I will do the actual derivation of the radiation. Second class, I will do the angular distribution. Third class, let's say a frequency dependence, like in what direction should you aim your radio antenna so that it's usually not like it's very directional. So we'll get that. And in the last class, I would like to do, hopefully everything goes well smoothly, then what if you, even though we cannot go faster than speed of light in vacuum, we can go faster than speed of light in a medium. That's possible. Like a fighter jet can go faster than speed of sound. So similarly, a particle can go faster than speed of light in the medium. Not, so Einstein only says that in a vacuum. So what will happen in that case? Usually there is a shock wave, like that's what happens in sound when fighter jets go faster than speed of sound. So we talk about that here, and that will be called Cherenkov radiation. And probably, I think some of you guys said that you have seen it. So I think we're all wrong, right? Yeah. So you might be able to connect with that, yeah, or visibly see the blue light or have an insight for the blue light. Yeah. So hopefully all this goes well. We'll see. I'll be a little fast, like today, basically. Yeah. Or basically, you guys allow me the 10-minute extra. That would help a lot.
So I have a quick question. Is it the
Yes.
same, is it the same logic when you say, when you look at the retarded potential versus the advanced potential, where you can mathematically talk about the advanced potential, but it's not necessarily a possibility? Is that the same as the light in a vacuum versus light in a medium?
No, that will be slightly more than that. Slightly more than that. There will be frequency dependence, and there will be some gymnastics in mathematics we will do. So at that time, ask me which I will be able to relate better instead of asking now. Yeah, you're asking, is it exactly the same as going in advance? Probably, my guess is not. Probably not. But maybe you have a point then. Yeah, I'm not completely able to see the situation.
Okay, thank you.
Okay, good. Yeah.